Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question, the rightmost nodes of a binary tree. It's a DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that return an array containing the values of the rightmost node at each level of a binary tree. And we are given this binary tree as an example right here. So this is the binary tree as you can see it here, and then the output is an array that corresponds to the value of the rightmost nodes at each level of the binary tree. As we can see here, this one level of the tree, this one level, this another level, so as specified by this arrow, these are levels. So and then the rightmost level at this particular the rightmost node at this particular level is the root node, which is node 1, because it's actually the only node in this level, so it is the rightmost node in this particular level here. So and that's why we have the node value, which is 1, printed added to the array. And similarly, when we move to the second level here, right here, so we see that the rightmost node is node 3, and node 3, the value is 3, right, and that's added to the array. So similarly, we do that on and on and on. Moving on to the next level here, we have the rightmost node to be node 6, and we have the value 6 there. And moving right here again, we have the rightmost node to be node 11, and that's why we have 11 here. So this is simply what this problem wants us to solve. At first, the solution to this problem might just seem as simple as traversing the rightmost node until we get to the leaf node. Look at it now. By traversing the rightmost node until we get to the leaf node, so and then at each rightmost node like that, we'll just be appending it into a list. But it is not actually correct, because consider if we do that now, and we first dive into the right node of this node 1, which is the root node. Fine, we're gonna get to node 3. If we append it into the list as well, we append 1 into the list, we append 3 into the list, and also append 6 into the list, we will see that we are going to be missing 11, which is meant to be inside the expected output. So that means that that's not an efficient way of solving this problem, because if we do it that way, we probably are going to be missing some node, just like in this case whereby we are missing node 11. So this means we need to consider the entire tree in order to get the expected output. So we're not just going to consider the right node alone, but we're actually going to consider the whole tree, because look now, if we are to get this correctly, definitely we must not only be considering the right node, which is node 3 and node 6 here, we must also consider node 2, which is left node, because we know that the node 11, which is actually one of the expected outputs, one of the expected value, because it is node 11 here is the rightmost node at this level 8, 9, and 11. So and it belongs to it is a descendant of node 2. So therefore, we are not just gonna consider the rightmost node or just a particular part of the tree. We are considering the entire tree to figure out all the rightmost node, the value of all the rightmost node, so as to get a very correct and complete solution. Fine, we know that BFS traverse a tree, a binary tree, level by level. So you can check my previous video, the immediate previous one on YouTube, on my YouTube channel, that's my YouTube handle. You can check my previous videos. I've done quite a number of videos whereby we treated tree related problems, DSA problems, where we consider the DFS, which is the depth first method, and search method, and the BFS, which is the breadth first search method. The depth first search method uses and utilizes recursive stack by recursion. It's going to traverse the tree by recursively calling the left and the right of each node, right? But the the breadth first search method is going to traverse the tree level by level. So it's going to consider this first level and this second level and this third level and this fourth level, right? Okay, you can go back to my video for more explanation on that, and also you can stay tuned on this video. You are still gonna understand it. Okay, so but one thing about BFS is that even though it's traverse the array and the tree level by level, it still does not have an explicit marker that tells us when a level starts and when a level ends, right? Fine, it's gonna traverse it level by level, but it doesn't actually have a standard method. The standard BFS doesn't provide an explicit marker to tell us that okay, this is the start of a new level or this is the end of a new level. Now, in contrast, there is a type of BFS, a custom made one, that will allow us to traverse the tree level by level, and will enable us to keep track of when a level starts and when the level ends, and this is the level order traversal. The core idea about level order traversal is that at any level of a tree, the children of the nodes at that level is what comprises the next level, right? Okay. What I'm trying to say in essence is that consider this particular level now. Don't forget this one level here, this one level that comprises of only the root node because it's the only node in this level. And then at this particular level, the children of all the nodes at this level, which is just node 1, is what will comprises the next level. And you can see it, I think it's very much explanatory because at this particular level, this is the only node, right? So its children are left children and right children, which is node 2 and node 3. So this node 2 and node 3 is what comprises the next level. So that is how level traversal works. So at any particular level that we might be, the children of the nodes, look at this level 2 now. Let's say this is the level we are. The children of this of the node at this level, which is node 2 and node 2. Let's consider the children of node 2. The children of node 2 is node 4 and node 5, and similarly the children of node 3 is node 6, right? So now it means that the children of node 2 and node 3 and any other node that is in that current level is what is going to is what's going to determine and define the next level that we are going into. To see how this works, let's consider this particular tree here below, and let's initialize our queue. Don't forget BFS uses queue, so let's initialize queue with the root node, which is actually the only node, the first and only node in the first level. This is the first level and it comprises only of the root node. So now the children of this root node is going to make up the next level, just like I said in the logic. The children of this root node now is gonna make up the next level. So what we do is that we're gonna pop out this root node. So because fine, it is the only node in the first level, so we're gonna pop it out, and popping it out, we're gonna push the next node, its children, both left and right children. We're gonna push it into the queue. So and you can see here basically that now the queue, after we pop out one and appended the children of the node 1, which is the root node, into the queue, we see that the queue now consists of the second level. Why? It consists of the it consists of the next level, which is the second level, because now it contains nodes of the next level, which is level 2. So and this is what I'm trying to say here. Look at the queue is now made up of node 2 and node 3, which actually is the level 2. So now the size of the queue is size of level 2, which is just 2 nodes. Since the size of the queue is 2, and that indicates that the whole level 2 actually consists of 2 nodes. So let's pop up the both node. So we're gonna pop it off one at a time. So being sure that the moment we pop up to 2 nodes, then we are able to navigate away from the level 2. Why? Because level 2 actually have 2 nodes, right? And the queue also contains 2 nodes, where the both nodes are actually node of node level 2. So once we pop out of our queue 2 times, I mean when we pop the first node and the second node, we are quite sure that now there's no more any node corresponding to level 2 in the queue. So doing that now, we are first gonna pop out the first node, which is node 2. By popping it out, we're gonna add a children node. Don't forget that we are trying to navigate downward. I mean, we're trying to navigate to the next level. So when we pop out in the node 2, what we're gonna do is that we are gonna add its children to the queue. So don't forget how queue work. Queue is a first in, first out. So this one will be added to the back. So that's why it seems to be added to this side like this. So we're gonna add node 4 and node 5, and we're gonna push them into our queue while we pop out 2, which is this node 2 away from the queue. So similarly, we're gonna do the same for node 3. We're gonna pop out node 3 from the queue, right? And in the process of popping out, you're gonna add node 6, which is just its child. Node 3 has only one child, node 6. So we're gonna push that child into the queue. So now you will see that we have essentially and efficiently navigate to the next level, because now you will notice that at this point, you will notice that at this point now there is no longer any node in the level 2, and all the nodes are now corresponding to level 3. Let me make this one this. Let me make it this, right here. So you see, now we are efficiently at level 3 now, and you will see that the length of our level 3 is exactly the same as the length in the queue. So what we just need to do now is that we have to iterate and pop the queue. We have to pop the queue 3 times. So we are quite sure that by the time we pop the queue 3 times, I mean we pop nodes out of the queue 3 times, we have efficiently remove and navigate away from level 3 to level 4. So by popping out of the node 3 times. Don't forget that each time we pop out, we are actually going to add in the children of the node we pop out. So we're going to add it into the queue. So but we already know, before we start popping out at all, we already kept track of the length of the queue. So making sure that we know that the length of the queue is the length of the nodes at level 3. So when we just have to pop out 3 times from the queue to be sure that okay, we now have we have now gotten to a new level, and we have all the nodes at level 3 removed from the queue. So to summarize this whole logic that we just explained is into 3 steps. The first step is that we first of all want to determine the level size. Why we need to determine the level size is because the level size is what we use to keep track of the number of nodes at a particular level. So that way we can keep track of the number of nodes at that level. We can pop out of the queue that number of times, and therefore we can be sure that the remaining nodes that we have in the queue corresponds to the next level. So it's important that we determine the level size. We collect the current size of the queue to find the number of nodes in the current level. Initially, at first, the queue will only contain the root node, indicating the first level of size 1. So don't forget that for any tree, it will definitely have a single root node. So and that's the first level containing just one node. So that's it. For the second process, we are going to process the current level, and what we mean by this is that for each node at this level, we will pop it out of the queue and add a children to the queue. Okay, fine. We said that for the very first time, initially, we are going to populate our queue with the root node because that's the only node in the first level. Now, because of that, we are going to keep track of the level size, which is going to be 1, right? Because there's just one element or one node in the queue, right? Fine. And then the next thing is to process the level by popping out that same level, that same number of time as the level size. The level size is 1. Level size is like a variable that we use to keep track of how many nodes are currently in the queue. So, and then that level size will be 1 because initially we just have one node. We have one node in the first level of the tree, which is the root node. So what we want to do is that we want to process the current level by popping out. I mean, we have a queue, right, and this queue contains nodes, fine, and we have the level size that help us to collect the current size of the queue. So, and we just have to pop it out that number of times so that we can be sure that every node in that level has been popped out, and every node that is still contained in that level now corresponds to the next level. Why? Because as we are popping them out, we are actually adding their children back into the queue. So, and what we do is that we just repeat step 1 and step 2 so to process the next level. And what we mean by that is that after we must have popped out that number of times as tracked by the level size, after we have popped out, we are sure that all the remaining nodes, after popping out, we are gonna add the left and the right. I mean, we're gonna add the children of those nodes that we popped out. We're gonna add them back into the queue, right? Don't forget, if you go back to the logic I explained, we are always gonna add them because we are trying to pop them out so that we can get to the next level. And how we can get to the next level is by actually adding their children into the queue. So after popping out that number of times, we are sure that the whole length of the queue at that point is equals to the length of the node in the next level. I really hope you understand. In the process of popping out 2 and 3 now, we appended the children of 2 and children of 3, and after popping out 2 and 3, we are quite sure that the length of our queue is now 3, and those 3 corresponds to the nodes in the next level 3, right? Just as you can see here is 4, 5 and 6, so it corresponds to the length of the node in the next level. Okay, so and that's it. You just keep on repeating that step, iterate through it that number of times, pop out, add, keep track of the level size again, iterate through it until every node has been added into the queue and every node has been popped out. So then at that time the queue is gonna be empty and whole level has been processed, and because of that we can now exit the loop. So, and that way now we are now left with how are we gonna get the end of a particular level. Fine, we are gonna get it this way. Since we are able to track the current size of the queue, I mean at the beginning of each level we are able to get okay, this is the size is 1, and after 1 have been popped out, 2 and 3 is added, and we can keep track that the size is now 2, and after 2 and 3 are popped out, 4, 5, 6 will be added, and we can now see that the size is now 3. So that way now, if we are iterating 3 number of times now, so that we can pop out all the I mean consider this 4, 5, 6 node now. If we are gonna be popping out 3 number of times, right, so as to remove 4, 5 and 6, we can easily determine, because we know that the length is 3, we can easily determine that okay, when we have gotten to the last node, which means what, node 2, I mean if we are iterating through 3 times, we are gonna be saying something like this: for I in range of 3, right, range of 3. If we are gonna be popping out 4, 5 and 6, then we need to do something like an iteration like this so we can pop it out. So definitely we can keep track that okay, once it has gotten to the end, so simply by saying that if I is equals to len of no, not len, level size minus 1, then definitely we do anything we want to do, we add it to the we append it to the stuff that we want to append it to. I mean we append that particular node value. Why? Because at the point, level size actually corresponds to 3, right? Level size is this 3 that we have here. It actually refers to the length or the number of nodes at that particular level. And then if I equals to level size minus 1, don't forget I is an index, and index are 0 based. So if the level size is 3, then I will stop at 2, 0, 1, 2. So once I becomes level size, which is 3 minus 1, then we want to do the append. We are very sure that that's getting to the very last node in that level. So this is simply how we're going to be solving this problem, and I really hope you do understand it. We'll be going to the code implementation now, and you're gonna understand it better there. Alright, Alright, let's dive into the code implementation for the rightmost nodes of a binary tree problem. We will of course be defining the tree node, right? The tree node now, don't forget, it just representing a class for the nodes, so that we can create node instances, just like node 5, node 6, node 1, node 4. So that's what this is actually what this is meant for. We're going to be passing the value attributes, so because it's a quite essential in defining a node. So a node do have a value, so and then a node optionally we have a left, but if it doesn't have, we're going to set it to none. What we're just trying to say is that the left attribute, or let me say the left child of the node, so it's going to be set to none if it doesn't exist. In a situation whereby that node is a leaf node now, so it's going to be set to none. Also the right node. So right here is our node definition: node 1, node 2, node 3. Just like you can see in the screen, on the screen you will see that that structure actually have node 1 up to node 11. So this is it. Similarly, we should now be having the connection between nodes. So just like you can see also on the screen, you will see that node 1 have a left node to be node 2, and it has its right node to be node 3. Similarly, node 2 have its left node to be node 4, right node to be node 5, node 3 have its left node to be node 6. So that's what I define right here. So I'm just trying to clone that structure in code formats. Okay, so having done this now, let's proceed to define our function. At least we now have the root node and we have the node structure, so we can define our function that we want to use to find the rightmost node of the binary tree. So we'll be passing in a node to it, which is actually a tree node, right? And actually want to return an array, which is a list of integer, right? So fine. Okay, in solving this problem, we'll be needing to import something from collections. We want to import the queue, DEQUE. So we're importing the queue, and the queue is just simply like a queue. It's actually a queue. So but and it has some added functionalities, like you can pop left. Don't forget that a queue is actually like an array, simply an array, but instead of having to pop from the end, which is that popping from the end is the last thing first out, which is not actually what a queue does. A queue, we want to pop from the left, not right. Sorry, it's not a queue is not gonna pop from the right, it's gonna pop from the left. Don't forget that in an array now, when we append, it's gonna keep appending it to the right. So, and when we pop, it's gonna pop it from that same right. But a queue needs to pop it from the left, so that the leftmost one will go out first. That's how a queue works: first in, first out. Right. So okay, now that we have we are gonna be defining the queue now. The queue object, let me see the queue variable. So it's gonna be using the queue functionality, and we are gonna pass in the root node to it, right? So you might be seeing this. What it means is that we actually want to initiate our queue with the root node, which is actually the first and the only node in the first level. If you look at the structure, you see that the root node is just the only node in the first level. So that's why we are initializing our queue with the root node. So in fact, let me call it the root node. Let's call it the root node. So we know that what we have here is the root node. So okay, so while queue, don't forget the condition is to what? Keep on the loop until there's no more node in the queue. And what we want to keep do is that we want to evaluate level size. The level size is equals to, first of all, don't forget from the logic, first of all we find the length of our queue. So knowing the length of our queue, now we can easily iterate through the queue over that particular length, so that we know that at that point at that point whereby we iterate through the length of the queue we are gonna pop out, and that's what we want to do now. So want to pop out the queue, queue dot pop left, so that I can pop the very first one, not just popping the last one, but it has to pop the first one in the order in which they enter into the queue. So, and now that we pop it out, what I want to do is I want to check if I is equals to length of our level, let's call it the level size minus 1. So this way we are trying to check if this is the last index in the level size. I mean, if this is the last if this is the rightmost node or the last node that are going to be popping out corresponding to that particular level. If it is, we want to add it into our results dot add node dot value. So definitely we'll be defining a result array, so whereby we're going to be adding. So simply what this one is just doing is that, you know, we have the length of our queue as level size now. So and if this as we iterate through this length of our queue, let's say the length is 3. Once the levels, once I, which is the index, once it becomes 2, that is, it becomes 3 minus 1. So we want to append the node at that particular current node, that which it becomes 2. Want to append it into our result, because we are quite sure that that is the last index. Don't forget that when we are saying range of 3, it's just gonna do 0, 1, and 2. It's not gonna do 3, because it's not going to count 3. 2 is the last one, and once I equals to level minus 1, we know that's the last node, we have to append it. So what we're going to do now is to check if node dot left, if node dot left exists, we want to add it to the queue dot append, so node dot left. So similarly, we want to check if node dot right. So why we are doing this is because don't forget that we are trying to process the next node. Now we have popped out this particular node. We want to add all the children into the node so that it can represent the next level, right? So, and that's why we are doing all of this. Queue dot append node dot right as well. It does if node dot right exists. So simply, this is what we'll be doing. And after the whole loop have ended, we want to return results. So it might just look simple. It's just as simple as this. So we can call it. I really hope you understand what we just did here. So all we just do is to first of all determine the size of the length and the size of the queue, then iterate through that same size so that we can keep on popping out each node in that particular level. After popping it out, we try to keep track of the very last one and append it, the very last node, which means the rightmost node. We do append it into our results array. Then we try to check if this node has the left child, and if it has the right child, then we append it into the queue. So, and then we are gonna keep doing that until there is no more node in the queue to process again. So but at that time, all our results and the result array will contain all the rightmost node in each level of the tree. Okay, let's run this code and see how it goes. Oh, so sorry, we have a syntax error right here. It's supposed to be a column. It's a mistake. I go put a semicolon instead of a column. So let's see how it goes. Fine, we have from 13611 returned, which is actually the answer that is supposed to be. So look at the problem statement. You will see that that's the answer that is returned in the problem statement. So because node 1, node 3, node 6, and node 11, node 1, node 3, node 6, and node 11 are all the rightmost node in this tree. So I really hope you understand this, and thank you so much for your time. Do well to subscribe to my channel, please. Do well to follow me on LinkedIn, on TikTok, on Facebook. I post each and every one of these DSA problems on each of these platforms. Okay, thank you. Do have a nice day.